This happens every year. It's getting to be the end, and inductors are one of the last looming topics in C, and students are out a lot or mentally out a lot. It's okay. I'll try to keep it simple here. Inductors are basically like toddlers. I'll explain in a second. And capacitors are going to be kind of like parents. So the short version is that an inductor is a curl of wire. And if you try to change the current going through the wire, that can't happen instantaneously. And this inductor or curl of wire is going to oppose that change. They're kind of like toddlers in that if you try to change something really quickly, they do not like it. And it doesn't matter whether they were already doing it or they were doing nothing and then you try to do something, they get really, really mad. They basically throw a tantrum. So there's clearly a positive potential here, negative potential here, causing current to go to the left. Now, as that goes around this loop, if you were to use your right hand rule and curl your fingers, you would get a magnetic field that's now going to the right. It's not actually the current that matters, but rather the change in the current. If you try to change that current, what that's going to do is that's going to cause an opposing voltage or a back EMF according to Faraday's law of induction. So that back EMF is negative the rate of change of the magnetic flux with respect to time. And I'll explain that in a second. But what that's going to do is that's going to try to create an opposing magnetic field, in this case to the left, that's induced. And the quicker you try to change this current, the quicker that induced magnetic field. So I liken it to toddlers, because toddlers, if you're really sneaky as a parent and you're really slow, you can get them to do something. But let's say you want to get out the door in the morning, that is the hardest thing in the world. Toddlers hate that. But if you just sort of sneak them out and make them think that they're going to eat a snack, or you distract them in some way and take a long time, they eventually go with the flow. And that's basically what inductors do. So let's talk about this Faraday's law thing for a second. The orange thing here is actually a curly straw I got from my kids, one of my kids' drawers that they keep their little kid spoons and stuff in. It's kind of funny because the kid's a toddler and I'm using them like a prop. So here's the same curly straw looking from the right here. So it's as if the current is going like that. Let me switch to blue. I like blue. Like this, and around like that, and curling around counterclockwise as we look at it. The magnetic field, the red here, is going to be out of the board towards us, or out of the screen. And remember, if it's a perfect inductor, one with more than 3 circles, it's going to be uniform within and no magnetic field without. And that's fine until you try to change that current. So if you try to increase the current, I guess I use the word. If you try to increase the current or increase the current here, what that's going to do is create an opposing magnetic field, basically like this. Now it's smaller than the existing magnetic field, and the faster you try to change that current, the bigger that opposing magnetic field is. Now, when we're talking about change in flux, let me just remind you that flux, or magnetic flux here, isn't exactly the same thing as magnetic field. Magnetic field is in Teslas. Magnetic flux is in Tesla meters squared, or Webers. Formally, you're taking the integral of B dot dA. So I tell my students there's 3 ways to change magnetic flux. You can change the magnetic field, which is what's going on here. You can change the area, and in this case that's not changing because that's just sort of around this circle here on the right. Or you can change the direction between them. So we're changing this magnetic field as we change the current. That's what's different here. But when you do that, it's going to create a back EMF. So it's as if I switch over to green here, this inductor is acting sort of like a mini variable battery that is trying to cause a current to go from left to right here and trying to oppose that current. There's no actual current going back, but there is a back EMF. The voltage across this inductor is different than it would be if it was just a wire. So initially, the inductor really, really doesn't want you to change anything, and it fights you fiercely. And then, because it has fought you, it has managed to slow down the current. Because there's less current, the magnetic field is weaker. And because the magnetic field is weaker, the rate of change is slower. And so the induced electric field, or the induced voltage, is lower. And eventually what happens is it's like a toddler in that you can wear them down, and eventually they will just go with the flow. So if we were to graph the current, and I can derive this in another video, but the short version, and this isn't seeming so short, if this was current versus time, in the beginning it's fighting you fiercely. So there's no current, and then gradually it's conceding, and by the end, this inductor acts just like a wire. The current just passes through uninhibited. There's no back EMF. So if this is a simple, say, RL circuit, the current is going to end up at a value that's as if the inductor wasn't there. If it's just a wire, it's going to be the E over the R, meaning the battery voltage over the resistance, the resistor. Let's contrast that for a second with what goes on in a capacitor. So in a capacitor, it's kind of similar in that you may want current to flow here, but capacitors are different. They're a little bit more like parents. Initially, if the capacitor is uncharged, it offers no opposition whatsoever. But then, as the charge builds up, it starts to oppose the current. So as you start to build up charges, sorry about that. So I think it's recording. So as the current continues to flow, it starts to build up these charges. It's almost like your parent noticing, wait a minute, something's changing. And what you're doing is you're building up an electric field, and you're opposing this buildup in current. So the current starts to drop. And if we were to draw a graph of the current from a capacitor in an RC circuit, and you're looking at the current and the time, initially, current flows fine. It's got no issues whatsoever. But over time, it decreases. And by the time your parents are on you and they are fully charged, you are not getting by. They are completely opposing. It's sort of the opposite of inductors, right? Like inductors notice right away. Kids watch you immediately. If there's any change, they're going to resist it. Here with capacitors, they're busy. They might not notice. If you're going to have shenanigans, the point is to get the shenanigans through quickly. That's the way a capacitor works. But the current is going to be very high and go to zero. Now, as far as the relationship, and we can derive this in another video. I don't want to take that much time. But for a capacitor, if you recall, if there was no capacitor and it was just a wire, the battery voltage would just be Ohm's law, E over R, the battery voltage over R. But because there is a capacitor, this current is going to decay, and it's going to decay as minus T over RC, or sometimes this is called tau, the time constant. For inductors, there's something really similar. For an inductor, it's really similar. You've got E over R. That's the current that you would get if there was just a battery and a resistor. But instead of exponential, it's going to be 1 minus exponential because it has to start at 0. So E to the minus T over tau. Now, you can write it as over tau, or I actually prefer to write it as R over L. Some people will say the tau L is L over C. The point is, there's a constant there that depends on the inductance. Oh, it should be R. The inductance and the resistance, similar to the time constant for the capacitor, dependent on the resistance and the capacitance. And you're going to get this sort of 1 minus an exponential decay. Lest you think the comparisons end there, no. There's this concept called capacitance, and capacitance is basically a ratio of charge to voltage. For a given number of volts, how many coulombs of charge can you store on the capacitor? It's charge per volts. Now, in terms of a physical capacitor, the amount of capacitance of a given capacitor, at least parallel plate capacitor, depends on the area, the distance between the two plates, and the permittivity of free space, epsilon naught, this constant. So you wind up with it just depending on the geometry of the capacitor. It's like epsilon naught times some length. There's something similar for inductors. Instead of capacitance, you have something called inductance. But you don't have charge, so what do we talk about? Instead of charge, what we're going to talk about is the magnetic flux. Now, the magnetic flux, remember, because it's a coil of wire, you have multiple loops. So we add all of those, capital N, the raw number, per current. So the magnetic flux is sort of like, or the inductance rather, is sort of like an amount of magnetic flux for a given current. You could almost think of it like, how strong of an electromagnet am I going to get for a given amount of current? In terms of units, remember flux has units of Webers, so that's Webers per amp. And a Weber, if you recall, is simply a Tesla times a meter squared per amp. But like many things in physics, we have shorter names. This is a Henry. It's an amount of magnetic field. Now, for a solenoid, before I forget, I did want to point out that this part here is often referred to as the flux linkage. Again, how much magnetic flux you're going to get for a given amount of current. We'll derive it in another video, not that it's that hard, but the inductance for a coil is mu naught little n squared L A. So this little n is the number of turns per unit length. The little l is how long the coil is, and the A is sort of this cross-sectional area here, like in this circle. But again, notice, what does it depend on? It depends on the geometry of the inductor. It depends on how long it is. It depends on the area, and it depends on the total number of coils. Which still makes you wonder, what's the point of an inductor? On the one hand, you can use it like in AC circuits to change. There's a lot of things with timing where you're affecting the time in a circuit with some combination of inductors, capacitors, resistors. But ultimately, what inductors do is they store energy. And that's a lot easier to see if we take a second and look back at capacitors. Now recall, in capacitors, there's an electric field between the two plates. So for you to move a charge from one place to another, you have to do work against that electric field. They store energy. And the amount of potential energy stored in a capacitor depends on the capacitance, and it depends on the potential difference. Or sometimes you'll rearrange these two equations and you'll get a useful version, which is that the potential is 1/2 QV. So in capacitors, we're storing energy in electric fields. In inductors, we're going to wind up storing energy in magnetic fields. So the amount of potential energy stored in an inductor is 1/2 Li squared. So the value of I does matter. The more I you have there, the more energy you have stored. And that makes sense, because to get to zero current, you're going to have to change a greater amount of current. So there's more energy in there. But now that we know a little something about inductance, the back EMF from an inductor is negative d phi b dt, but that's going to be the same as negative L di dt. So even though I'm not doing it now, if you have to do some sort of problem with inductors, you may have to do one where you loop around the circuit using conservation of energy. And remember, the voltage is going to oppose the change, and it's going to have a magnitude that's negative the inductance di dt. By the way, you've probably noticed this effect if you've been alive and you've been in a place where there's a big motor, for example, a refrigerator, particularly an older one, or some other motor that has presumably some large coil in there, some motor or something. And when it first turns on, when you're going from no current to a big current, that is a big change. So initially, there is a large back EMF, and sometimes that can actually make the lights and other things dim. I've also heard, I don't know if it's true or not, that many fans are actually wired so that when you turn the knob, it first goes to low instead of high. This way it's a lower change in current and hence a smaller back EMF. I don't know if that's true or if I'm making that up. Somebody might know the answer to that. You'll also sometimes hear about inductors as a low pass filter, meaning if you have a signal going back and forth, and as long as it's changing slowly, it can go through the inductor. If it goes slow enough, it basically acts like a wire. But if you try to have a fast, high-frequency signal go through, it's going to be sort of filtered out. There's like a response. With capacitors, it's the opposite. If you have a high-pass filter, it passes through no problem. The reason being there hasn't been much time for charge to build up on these plates. But if you try to have a low frequency, it gives time for the charge to build up on the plates and oppose that change. So inductors are like toddlers. They fiercely resist any changes in current with a back EMF. And toddlers are like parents. You can get shenanigans through quickly, but you can't give it much time for the charge to build up. I have no idea if this toddler thing makes sense to you or not, or if it's just really close to me because I actually have a toddler and an older one. But I hope to somebody out there that this was remotely useful, learning a few things about inductors.